Hi, Tim. So today we're doing a two-part practical. We're going to do the first part today and the second part tomorrow. 2 parts. Wonderful. So, some learning outcomes. We're going to investigate how the resistance across different lengths of wire varies. And this is the application of Ohm's law. Okay? So, here we go. Backup information can be found in your Caboodle textbook on pages 48 and 49. I'm sure you all know how to get to it by now, but if you're struggling anyway, email me. I'm lonely. I've had very little science work this week. So, resistance. How difficult is it for current to go through part of a circuit? And we need to give some example apparatus or equipment. So here is my lovely diagram. I've got my power pack, my ammeter measuring current, and my voltmeter measuring voltage or potential difference. The voltmeter measures potential difference. It's like I've written the slide. And the ammeter measures the current. The meter stick measures the length. Exciting stuff. So, along the meter stick, I have a piece of wire that is screwed to the stick. And we've got some crocodile clips that I can then move the voltmeter and ammeter along to work out different lengths. So what is the point of this practical? I do ask sometimes. However, it's to find out the resistance of a wire. All different metals have a different resistance. Different metals allow different amounts of electrons to flow. And this is to do with their structure. If you look at the different lengths of wire and different thicknesses or even different temperatures, you can see how this impacts on the flow of current. There are 3 variables within this practical investigation: the independent, the dependent, and the control. The independent variable is what we change, and that is the length of the wire. The dependent variable is the current, okay? And the control variable, it's lots of things that you can keep as the control variable, and they all have an impact on the resistance of the wire. So we need to keep the temperature the same, because obviously you need to relate that to kinetic theory. If it's warmer, the wire can melt, as not that I've ever messed that up that badly, but yes, it can melt, catch fire even. But more importantly, other than that, the metal molecules can move around, metal atoms can move around and cause and have an impact on the resistance. The thicker the wire, again, if a wire is thicker and it's got a larger diameter, it allows more current to flow. The type of metal, which I've already talked about, and the potential difference needs to stay the same. You need to be able to explain each of those variables. So when all the control variables are adequately controlled, you're only measuring the change in the independent variables, and that is really important. That means that our results are comparable to each other. So, the method. There's your diagram. You should be able to label that diagram, by the way. Sketch it out. Test out your art skills. Find a pencil. And here is your method. 5 steps. Have you noticed that we started blocking things in 5 steps to give you a better chance of remembering it? What I want you to do is try and reduce those sentences down as short as you can, just so that you can remember them. So hazards. The heating of the resistance of the wire. It can burn skin. Have you got to think about this? Lots of surgery is done with a heated wire. It's quite dangerous. Also, the whole thing is risk of electrocution. Not mentioned there, but it's quite real. Not that I've done that to myself at all, I promise. So, here is my method. We're going to set up the equipment, tick. Set the length of the wire to 100 centimetres, tick. Then we're going to set the power supply to 1.5 volts, tick. And then we're going to record the readings for the voltage, the potential difference, and the current, tick. Then we're going to repeat them for different lengths. Now you need to give a range of 5 readings. So you're going to need to say, I'm going to do it at 10, 20, 30, 40, 50. That's 5. Or you can say, I'm going to go 20, 40, 60, 80, 100. That's fine. But we need a set of at least a range of 5 variables that you are going to test. especially if you're aiming for those 5s and 6s in the exam, which I hope all of you are, because you are genuinely awesome. Okay, so here we go. So the results may look like this. I feel like I should have some music for this bit. So these are some I did earlier. It's Blue Peter moment. And we can apply the equation linking voltage and current, which is V equals IR. So if I divide the voltage by the current, it gives me the resistance. It's that little triangle that I really love. And then we plot our resistance against the length. Look at that, it's a beautiful graph. Beautiful. Now, if we've had any heating going on, that graph isn't quite that beautiful and it's not straight. You get a bit of a wobble in the middle. Again, I only have read about this, never messed it up that badly. And the evaluation from the graph, you can be seen that the longer the piece of wire, the higher the resistance. Voila! So therefore, we clarify that resistance is directly proportional to its length, and the graph gives us a straight line that goes directly through the origin. There cannot be any resistance if there is no current flowing. It is as simple as that, guys. It's got to go through the zero. Also, this is where they sort of try and trick you out on the exams. Very, very cheeky, those examiners. So what you need to make sure is when you're plotting this length, that you make sure that you start from 0. If you do start from 20, just make sure that your line doesn't go through the origin. But on this graph, they are particularly looking for this line of best fit, which is a straight line in this case, to be going straight through the origin. Okay, so let's move on. So here, resistance is equal to potential difference divided by current. Already said that. And the longer the wire, the more resistance. Tick. The thicker the wire, the less resistance is another fact that you need to know. And the higher the temperature, the more resistance. 3 interesting facts. You never know, in a pub quiz in years to come, this may be useful. It's probably been quite useful for the exam as well, by the way. So, what may they ask us about? Let me think. So, why must the power pack be kept on a low potential difference? What are the hazards? The wire could get very hot and burn you. From experience. Okay, there is also a risk of electrocution, still not mentioned. Okay, explain how the temperature affects the resistance. Oh, as the wire gets hot, the ions inside vibrate faster. Ooh, there are more collisions and the electrons cannot flow as easily. Think about year 7s. When I'm teaching resistance, I always talk about year 7s and corridors. If it's a really narrow corridor, it's much more difficult to get past those year 7s. If the year 7s have all been at the Red Bull in the drinks machine, they're all moving around, they've all got a lot more energy and they're in your way and it takes twice as long to get anywhere. So think about them, all right? And why is it important to switch the electricity off between each reading? Again, you need to allow the wire to cool down, okay? Some people talk about the wire cooling down and taking the temperature of the wire. You can be like that if you've got time, if you're looking for something to do with your spare time. All right, so lastly, what sort of error can cause the ammeter or voltmeter's readings to be too high? Now, they talk about this a couple of times in the exams, and voltmeters and ammeters are one of those places where this sort of error can occur. You can have a 0 error, and I'm sure that that's what I have when I get on the scales, because I no way weigh as much as it says. So basically, when there is nothing flowing through my voltmeter and ammeter, there is already a reading. Okay, and what you would need to do is either reset it, okay, which would be the perfect answer. You would reset the ammeter to 0. And those of you that have managed any of the quality equipment we have in school, that's when I get a biro and shove it in the little button underneath. However, if you haven't witnessed this, you just need to say, I will reset it to 0. Or if you realise this at the end, which occasionally does happen, what you can do is minus that original value off of your final value to work out your 0. But the exam board don't really like that explanation. They really want you to talk about resetting it. And the resolution of measurements, the repeatability and reproducibility and control variables. So the resolution of measurements is the smallest size measurement that you can make. So if my ammeter is 0.00 on the screen, the smallest resolution of current that I can measure on my ammeter is 0.01. Repeatability, minimum of 3 repeats. That's what we need. Reproducibility and control variables we've talked about. Let's move on. Some useful links, okay? I would hate to think of you guys sitting at home waiting for one of us to produce another quality video and have nothing to do. So in that case, if you're bored and you would like some extra viewing material, here are 2 links. I will add those at the bottom just for your pleasure, really. And there is a SAM learning task associated with this. Awesome. See you tomorrow.